So let's go over these questions from your practice quiz for this particular assignment. And the first thing you're asked to do is find the area of this regular polygon, which is a regular octagon. So a couple things we're going to know about this regular octagon. I'm going to kind of superimpose a center here. I'm going to draw a couple of auxiliary lines that I'm going to make use of. And I'll draw one here. This angle right here, this central angle, is going to be 45 degrees. Because if I would form all of these triangles in here, I would have 8 of these central triangles that share equally 360-degree turns. So 45 degrees for that angle there. What I want to do is I'm going to try to use the formula that the area is 1/2 the apothem times the perimeter of the figure. Well, the perimeter, that part's pretty easy, because that's just going to be 8 times 14 centimeters, because I have 8 sides, each 14 centimeters, so that would be the perimeter. As far as the apothem goes, when I create, when I use this other triangle down here, now the apothem represents the altitude of one of these triangles that are formed. And so a couple things I do know, it's going to split this side into 2 equal parts, and since it's 14 centimeters, it's going to be 7 centimeters and 7 centimeters. And I also know that each one of these angles here is 22.5 degrees, because it's going to split that angle in half. The apothem is that altitude. So I could say that if I do a trig function, now depending on which trig function I want to use, I mean, I could put other things in here, but I'm just going to use the 22.5 degree angle. This is the opposite leg. The apothem is the adjacent leg in that case. So if I have the tangent of 22.5 degrees equaling 7 over A, that means that A is going to be 7 over, I don't know why part of my A disappeared, 7 over the tangent of 22.5 degrees. So now I can come back up to here and finish off the question. The area is going to be 1/2 the ratio, if I get this thing to draw. Oh, it's going to want to have difficulty. There we go. 7 over the tangent of 22.5 degrees over that 8 times 14. And when I compute all of that out, I get approximately, and I didn't work it out yet, so give me 1 second here. About 946.37 square centimeters. So that's how you calculate that one out. I just want to double check something here. There we go. Okay, so going back to this. My computer's acting up, so bear with me. Okay. Now, as far as this particular situation goes, this is a circle, and they're asked to find a circumference, which is basically a circle's version of the perimeter in the area. From the markings we have here, we can see that the diameter, helps that this thing would do the commands I tell it to do. The diameter of this was given as 16 feet, which means that the radius is 8 feet. We often go for the radius because there's a formula for circumference as well as area to deal with radius. There's also a circumference formula that deals with diameter as well. But there is no formula for circumference in terms of diameter. So the radius is always something we always tend to look for. If we know the diameter, we always want to make sure what the radius is. But the circumference would be calculated pretty easily just by doing pi times the diameter, which they do give us, so it's 16 pi. And I could just say feet. And I could come up with a decimal approximation, but the way that the answer was given to you, this was the answer you were supposed to obtain. The area function, the area formula is pi times the radius squared. So in this case here, we have pi times the radius, which is 8 squared, which gives me 64 pi square feet. Always be aware of the units and make sure that you are providing the correct units, but that's all there was really to this problem here. For the next one, now you're asked, and one of the things you always want to make sure you know the difference between the measurement. Why does it keep doing that? Between the measurements of arcs and the lengths of arcs. Two different things. The measurement would be the degree measurement, and the length would be, of course, the length. So the first we are asking for the measurements of these arcs. Now the measurements of the arcs are equal to the central angles that they obtain. And whenever we see just two letters designated for an arc, we assume that we're going to be looking for the minor arc, not the major arc. Major arcs are always going to have a 3-letter designation. So when I go from B, when I say BC, I'm going right from B to C. So I'm talking about this arc right here for the first one. Just to give you an idea where it is. Not coming from in this direction and coming up to C that direction, because I would say that's either BAC or BDC or BEC, so I could indicate the direction that I am moving, so that I end up with at C last. But since the central angle is 50 degrees, this one's going to have a measurement of 50 degrees. As far as arc AC goes, and I'll switch to a different color. This lets me. AC is this entire arc right here, which does make up a part of BC. So I'm looking at this angle right here as its central angle, and I can see it's made up of 60 and 50, so it's 110 degrees. So this would be 110 degrees. Now, when they say the measure of arc ADC, I'm talking about this arc all the way around, because it's a major arc. So if I said arc AC, that's the minor arc. ADC is the major arc. And it stands to reason that the major arc and minor arcs together for AC here would have to be, total 360. So this down here should be 250 degrees. It's ADC, yes. All the way to here, 250 degrees. So that's the measurement of arc ADC. It's 250 degrees. Now they ask us for the length of arc ADC. Well, what I do for the length of an arc is I first take the circumference, which in this case here with a diameter of 8 inches, it's going to be, how do I put a 1 there? It's going to be 8 pi inches. The arc lengths are proportions of this. So since that arc represents 250 out of 360 of the entire circle, that's the proportion of the circumference this is going to be worth. And if I work that out, I would get 50 pi over 9 inches. And we often try to keep them in terms of pi if we can. The length of BCE. So let me erase some of this stuff here because it's kind of superimposing on themselves. So let's try to get rid of some of this. And that's why, like, if you're doing this, you should definitely redraw the figures and stuff like that. So the arc we're looking for here, BCE. Now we could probably just call this arc BE because it is a minor arc. But there's no harm in calling it BCE. I can see that this total measure here is 90 degrees. So for this case here, I'm going to be doing 90 degrees over 360 degrees times 8 pi. 90 over 360 is 1/4, so this is going to be 2 pi inches. Now, as far as areas of the sector go, it works in a very similar way as arc length goes. We're looking for, now, anytime they mention a sector name, and again, I'm going to do some erasing here because I'm going to need to do some calculations here. When it says BMC, the middle one's always going to be the middle of the circle. So when they say, okay, I want BMC, that means I want, basically this sector right here. And we're always going to be looking for the smallest sector. And why it doesn't want to color today. It's being naughty. Okay. So that's a sector I'm looking for. Now, when I do a sector calculation, it's going to be a proportion of the area. So I'm going to come up here and say, well, the area, and I want to have a pen, not a highlighter at this point. There we go. The area of this circle, since the diameter is 8 inches, I know that the radius is going to be 4 inches. So that's going to be 16 pi square inches. So this being 50 degrees of a full circle up here, if I get this, there we go, it's circling on one screen. Okay, there we go. I'm just going to keep carrying on with this recording at this point because part of it, for some reason, this computer is acting up today. So I'm just going to continue on with the calculations where I was. And where we were is that we were working on finding this arc right here, this sector. And me noting that two things. That the area before we were so rudely interrupted was 16 pi square inches, and I had a 50-degree central angle here, which means that I actually have 50 out of 360 of the circle area. So I'm going to take that times the area of the circle, not the circumference like I did the previous ones. And if I do that, I get about 20 pi over 9 square inches. AME. AME would be that sector plus these other two. So basically the area that this is encompassing is all of this as well. Just need to cooperate with me. So that entire, I can see that the central angle has 60, 50, and 40, which is going to be a total of 150 degrees. So when I do that calculation, I'm going to have, and I need to get to the pen, not the... So looking at this angle right here is the central angle. Be nice to distinguish right. There we go. Sorry about all this. I don't know why this thing doesn't want to cooperate with me. So I'm going to have 150 out of 360 times 16 pi. And that becomes 20 pi over 3 square inches. And the last sector, AMC, is basically everything. Let's just go to eraser with this. It's basically, again, just these two. If it'll actually do it. There we go. So the central angle is 110 degrees there. So when I do this now, I'm going to have 110 over 360 times 16 pi, which is going to give me 44 pi. For 9 square inches. So that's how you carry those through. For this one here, to do the area of a ring or anything that has like a space in the middle of it, I mean, I'm basically going to be doing the area. And again, I have to make sure that this is going to write. The area of the larger circle minus the area of the smaller circle. That's going to be the area that we're looking for here. I can see that the smaller circle has a diameter that's 10 inches, which means it has a radius that's 5. When I look at the larger circle, given that, this distance here is 3 inches, that means I'm going to be adding another 3 on this side, another 3 on this side. So its diameter is going to be 16 inches, which means its radius is going to be 8. And the reason why I need to know the radius is because the area of the larger circle is going to be pi times its radius, 8 squared, whereas the area of the smaller circle is going to be pi times its radius, which is 5 squared. So what I have is 64 pi minus 25 pi, which is going to be 39 pi square inches. So pretty straightforward there. And anytime that you have the area of something that has a gap in it, you're always going to be doing the area of something minus another area, which is the premise behind what we do with segments. Now, a segment of a circle is usually, if I have, we sometimes call this, if I can get it to write again. It's one of those days. this is what we would call a secant line, or secant segment. This here is the actual segment of the circle. It's basically, if I have one of these, I could call it a secant segment. And later in the textbook, which we're not going to really cover the term very much, it's called a chord. Basically, like, it's any segment that connects, that has endpoints on, has both endpoints on the circle itself. A diameter is a chord. It's just a chord that goes through the center. So if I have a chord, and whatever it's between the chord and the circle is bounded by that, that's what we call a segment of the circle. Now, how do we find the area of such a thing? Well, what we do to find the area of a segment is that we do the area of the sector minus the area of the triangle that we have formed, also as well when I look at the radii and things like that. So now both of these calculations are fairly simple, especially if you've worked on, especially in my course where I had students make sure they worked on, using the trigonometry to find areas, because, there's work you could do to figure out the area of the triangle. But it's a lot easier if you just use the one formula that we come up with, because we do have two sides in the included angle. Because the area of the sector, knowing that this is the radius, I know that the area of the circle is 36 pi centimeters squared. So for this, the area of the sector, it's going to be 55 over 360. Times that 36 pi. As far as the area of the triangle goes, we have a formula in that kind of circumstance where that's going to be 1/2 the two sides times the sine of the included angle. And if I work that all out, I get about 2.534. Yep. So that's all we have. So if there's any more questions, please feel free to, contact me or your teacher. But until I get to see you in a live lesson, or I get to talk to you on the phone if you're one of my students, I'll see you around. Have a good day.